So welcome to week 4 of our series. I can't believe we're already on the second half of our series. Thank you all for joining and coming in week after week. Whether you're watching it or participating live, or if you're watching it through videos, I think we've had just as many folks join us by video and take a look at those lessons and send emails and ask questions. So definitely a great way to get some new learning out to everyone. So this week we are going to focus on multiplication strategies. I'm going to share my screen. So we've focused on, over the last 3 weeks, we focused on kind of why we do the new math that we do. We focused on addition strategies, subtraction strategies. So this week will be multiplication strategies, and next week will be division, and then we'll have a final week where we kind of bring together all the routines. If you were able to click the link to get to the session today, then you also have access to all of the videos in that same document. Once they've been recorded, we put them right into that document. If you are watching this through a video session, then wherever you click the link for this video, most likely you'll find the links for the first 3 videos. We're trying to make them as easy to find and as user-friendly as possible. So when we think about multiplication strategies, we know that addition and subtraction show up as students need to have addition and subtraction strategies fluently by grade 4. Multiplication is fluently the standard US algorithm by grade 5. And we actually start to see multiplication a little bit in grade 2. It really starts to take off in grade 3. And then we build on those strategies for grades 4 and then get to that standard algorithm in grade 5. And so we'll look at kind of those progression of strategies today. And I hope that you'll be surprised by some of the strategies that you see and some of the manipulatives that you see students using for grades 3 and grade 4 and even grade 5. So often we use those manipulatives, those base 10 blocks or tiles. So often we use them in our kindergarten, first, second grade classrooms, and they tend to sit on the shelves for some of our older students, but really they're just as important for some of those students because it helps them build that concrete understanding of the strategy. So we'll look at where we might see base 10 blocks or tiles being used for arrays for multiplication. But before we get into that, I'm going to share with you the Graham Fletcher video from gfletchy.com around multiplication. We saw this for addition and subtraction. We also saw these videos for early number and counting progressions. So again, that's from gfletchy.com. And we will watch it straight from here, I believe. If you can't hear the sound, please let me know.
So here's my attempt to explain the progression of multiplication. Well, most of us might think it starts in 3rd grade, but in actuality, it starts in 2nd grade, where students are expected to take a square or a rectangle and partition that square into no more than 5 rows or 5 columns. Here, the understanding of repeated addition is established. 5 plus 5 plus 5 plus 5 plus 5 is 25. Then, in 3rd grade, students take that understanding they begin to develop in 2nd grade and begin to construct arrays using square colored tiles, or any manipulative for that matter. The important piece is once they've actually constructed that model, they draw a pictorial representation which matches their model. Here we have 4 rows of 6, or it could also be seen as 6 rows of 4, depending on how you turn the model. And the big piece here is that we don't push an understanding on students, we let students explain what their model represents. The big piece is that the context will explain the equation, not the teacher. Then we take that understanding and we come back to the biggest piece probably in 3rd grade, which is that there's a relationship happening here. And that relationship is taking place between multiplication and division. Take this, for example. 12 divided by 4 is a number. 4 times what number is 12? Well, if we take 12 tiles and we put them in 4 rows until we run out, we actually see that we have 3 in each row. So there's a connection between multiplication and division, and arrays can be used for both. The context. Yep, let's go back to it. Here's a simple one. There were 3 packs of pencils. Each pack had 40 pencils. Well, at the beginning part of multiplication, students might do something like this, where they draw out 3 circles, and in each circle they put in 4 10 rods, so 40. Or they could actually go ahead and draw 40 little pencils. That's great. But the standards of mathematical practice, and in particular number 7, want us to be efficient. And one way to do that is we can begin to make use of structure. And when we do, we make sense of it. Here we begin to create an area model for multiplication, very much like an array, just on a bigger scale with larger numbers. So 3 times 40, we take it, build it out of 10 rods. We have 10 tens, which is 100, plus 20 is 120. Or it could also be seen as 12 tens. Really big understanding for students. Once students have established this, they should be diving into drawing pictorial models for what they're concrete. Again, we don't want them to be sitting there with manipulatives all the time. So we move them away and they begin to draw a pictorial representation for what their concrete model looks like. Then from there, we'll have them use numbers to represent their picture. All of the time, connections are being made. Then, eventually, after multiplying all of these ones and tens, students begin to collect and group numbers together. Now we're beginning to become efficient thinkers. The connections are being made all around because students are exploring. In 4th grade, students are expected to multiply 2-digit by 2-digit numbers. So what does this look like with a concrete model? Well, it kind of looks the same, really. So we have 23 across the top and 22 down the side. 10 times 10 is 100, and that's where those 100 plates come into play. Then, once students have gone ahead and actually built a model, they see that they have 4 hundreds, 10 tens, 6 ones, and they add that all together, 506. Then just like we did with smaller numbers, we expect that students should draw a pictorial representation which matches their concrete model. You can see the 100 plates, the 10 rods, and the 6 ones. There they are. Altogether, 506. And just like before, we'll ask that students go ahead and start using tens and numbers to actually represent their model. So what you're probably thinking right now is this is not efficient. There's too many tens going on here, too many ones, and students are going to get confused. And you know what? You're absolutely right. And it's at this point where kids say, this sucks. We need to find a shortcut. So what do? They begin to group and collect their numbers, just like they did before. So here we have the box method. But in reality, it's partial products. So let's not call it the box method anymore and start calling it by its real name. Then we take that partial product understanding and we begin to formalize it into some kind of standard algorithm. Yep, this is a standard algorithm. It's a series of repeated steps. And you can see where each of the numbers come from. Then we have the algorithm that we're all pretty much used to. But you see that 0? Now the connection is made and students know why we magically put that 0 there. But all this understanding happens at the end of 5th grade. Let's not rush them. There's so much happening here and so much to explore. Let's slow down a little bit. Let's continue the conversation. Join me on Twitter, and thanks for watching.
So you can see there's a lot going on for multiplication, and we're not just jumping into that standard algorithm, putting in that placeholder 0 and following a bunch of steps. And I really, I get excited about multiplication because I feel like this is where we're really taking what students have learned in grades 1 and 2 with addition and subtraction, and we're using that knowledge to kind of build onto our knowledge of multiplication. So I want to make sure I'm in the right mode. So we're going to model some of these problems up here on our board. So we're going to start with students using repeated addition. So if I have the problem 6 times 3, as students are starting to learn about multiplication, they actually will start with repeated addition. They'll understand that this is 3 6s, and we're going to add those together. They may also see it as 6 3s. So it's that context of how students are understanding the multiplication problem. And in most cases, they'll probably see it as 6 3s, 6 groups of 3. And then they would add these up. So then they're seeing 6 plus 6, and then they can see, well, that's 12, plus another 6 is 18. Students start to skip count. We start to see multiplication happening by skip counting. And the facts that they actually start to build on, probably the easiest and the quickest, are your 2s, your 5s, and your 10s, because they've been counting by 2s, they've been counting by 5s, and they've been counting by 10s since they were in kindergarten. So they can count out quickly how many 2s it takes to get to whatever number. So if I had 2 times 5, 2, 4, 6, 8, 10, and they can figure that out pretty quickly. By 5s, they're counting by 5s, 10s, they start to learn those patterns pretty quickly. And once they have some facts built down, they actually will use these facts as helper facts. And most likely, they're going to use these 3 numbers and the facts that these are based on as their helper fact. So if I have 7 times 8, I might actually say, well, I know that 5 times 8 is 40, and I need 2 more groups of 8. So then they would add on another 8. 48, and then add on another 8 to get 56, and then we know that that's what 7 times 8 is. So they use what they know to then build up. They may have also said, well, I know that 7 is a 5 and a 2, so I could have said 5 times 8 is 40, 2 times 8 is 16, 40 plus 16 is 56. So they're starting to use what they already know. Students will also be using arrays. And so with arrays, they might use an array model, 5 times 4. So I have 5 columns and 4 rows. So I model this out. And I actually would start modeling this out with square tiles. Most classrooms have those multicolored, the red, blue, yellow, and green inch square tiles. And they use these tiles for a lot of arrays. And so they know that when it makes a rectangle with even numbers of rows, or even rows, not even number of rows, but even rows, they can make a rectangle, and they can make that array. And then this is kind of how it starts to build into those individual tiles. Eventually, you're not going to want to build out larger numbers with those individual tiles. This is where those base 10 blocks can come into play. So if I have the problem 12 times 6, I can model that out. We saw Graham Fletcher do that as a 12. A 12 is a 10 and 2 1s. A 6 is going to be 6 1s. And it doesn't matter which number goes on which side, because you're still going to be making essentially an array out of these base 10 blocks. So this is one of my longs. So we talked about base 10 blocks last week. We have our unit cubes that are 1s. We have our longs, which are worth 10. And when we put, we get into larger numbers, we have those 100 blocks. They're represented as a square. So in this case, I have 1 times 10 is equal to a 10. 1 times 10 is a 10. 1 times 10. So when we look at this, we end up with 6 tens. 1 times 1 is 1. 1 times 1 is 1. So essentially, if we just looked at this top row, we're saying 1 times 12 is 10, 11, 12. If we do 2 times 12, we have 24. And so when we continue to do this work, for our problem, 12 times 6, we now have 6 down the side here, and we have 12 across the top. We're making an array out of that 12 by 6, but this is a base 10 with a base 10 blocks with this model. We have 60, and we have 12 ones. We can group together these 10 ones for another 10. So we have 70 and 2 ones left over. So when they're using those blocks, you want them to be using the actual blocks. And I don't have base 10 blocks here at home, so I don't have the actual blocks to show you, but this is how students would actually model this out with the blocks before they get to the pictorial version of this where they're writing this out. Now, I will tell you, I never learned about the area model until about 7 years ago or so. I was working with some other math coaches and math leaders, and they were using this area model, and I went, why was I never taught this way? It's such a clear visual, and it actually leads really well into algebra. When we get into upper grades, they can use this area model in algebra as well. So once we get going with the blocks, we then may use the area model for bigger numbers. And we're going to now stick with the problem 32 times 26. And I'm going to model that out in the next strategies. So again, we can do that base 10 model. So we have 32 times 26. And when I multiply 10 times 10, I now get a 100 block. 10 times 10, 10 times 10, 10 times 10. 10 times 1 is 10. 10 times 1 is 10. Again here. Now I have 1 times 10 is 10. And we're going to do that. I'm going to kind of go all the way down through here because I'm seeing 10 times 1. 10 times 1, 10 times 1, 1 times 1, 1 times 1, and we do the same thing. So we can see that this really is not an efficient strategy, but it certainly makes students understand what it means when we multiply. We could actually count out all of these blocks, and they can see that our numbers, this 10 by 10, there's 100 here. And as we count them up, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm going to circle this group. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, I am circling them in groups of 10, but when you see these 10 here, these are 10 10s, so this is another 100, whereas this 10 is actually 10 1s, so it's a 10. So when we're counting up to find out how many total blocks we have here, we have 100, 200, 300, 400, 500, 600, 700, 800. We're going to look at our 10s. We're going to group those in with that one. That was part of that 10. So we have 10, 20, 30. And we have 2 ones left over. So again, it's not a real efficient strategy, but it's not about having students do all kinds of problems over and over and over again. It's really about taking one good problem and letting students work that problem out. So taking one or two problems in a math class that's an hour long is actually very beneficial for students rather than taking 20 problems and trying to rush through and follow a list of steps. So once we move on from this base 10 model, we're really going to get into those area models and make it more efficient. So again, we're going to use 32 times 26. And in this case, I'm going to jump us into this area model where we're going to break apart 32 into our tens and ones. So we're going to say 30 plus 2. And notice in this case, it's not to scale, right? It's not about being to scale, and that's why we're numbering. We put our numbers here so that we've labeled the work, but we don't have to actually have it to scale. And then on this side here, we're going to have our 26. So we have our 20 plus 6. Now we call this the area model because when we are finding the area of something, when we think about length times width, essentially that's what we're modeling here is we have our length and our width, or height and width. So we're building this rectangle and we're finding the area inside of this space, which is what we do when we multiply. So we have 20 and 6. So now when we're multiplying, we're looking at the parts. Here's a 10 times a 10. So 20 times 30. Students start to look at those patterns. They can see that this means 2 10s times 3 10s. They've already learned that that's going to be 600. And the way that they might do that is we look at this 20 is 2 times 10. This is 30, 3 times 10. 2 times 3 is 6. We have 6 times the 10 from here is 60. 60 times the 10 from here is 600. So often we say, multiply the first digit here and add the zeros to the end. The problem is we're not actually adding zeros, because when we add 0, the number doesn't change. And it's not this magic rule. The zeros don't just appear there. There's an actual reason why those zeros appear there. So again, if we think about this as 2 times 10, and this 30 is 3 times 10, if I'm multiplying these, I can say 2 times 3 is 6. 6 times this 10, or I could even say 2 times 3 is 6, 10 times 10 is 100, 6 times 100 is 600. So it's multiplying those pieces. And in multiplication, the order, students will have learned that the order that you multiply doesn't change the product when you get done. Much like addition, it does matter. The order matters in subtraction and the order matters in division, but they'll have learned that it doesn't matter in multiplication, and therefore they can pull apart these numbers and multiply them in an order that makes sense for them. So let's continue here. We have 30 times 6. So I know, well, 3 times 6 is 18, times that 10 makes 180. 6, and it doesn't matter which order, 6 times 2, I'm going to fill in this area here. 6 times 2 is 12. 20 times 2 is 40. And now I'm going to add up all my parts. I essentially broke it into chunks that I can now add together. So 600 plus 180 plus 40 plus 12. I'm adding the parts together to make the area for the whole thing. $832. So this process here, it's using the area model, but it leads us right into partial product. Now, if you watch the addition strategies, you saw us do partial sums. where we added together the parts, the hundreds and then the ones. In this case, we're going to multiply the parts. We're going to multiply the tens. We're going to multiply the tens and ones from one number, the tens and ones from the other number, and then the ones. So in partial products, students might not actually draw out the picture, but they can look at this 32 times 26, and they can say 30 times 20. They can say 30, because this is a 3, but it really is a 30 because it's in the tens place. 30 times 6. So again, that's right from here. And then I've got to come over here and I'm saying this 2, I've done everything with the 30, I've multiplied it by the 20 and the 6, and now I'm thinking 2 times this 2, 20. So 2 times 20 equals 40. There's my 40 from here. 2 times 6. And when I add these all together, I'm going to still get 832. So nowhere yet have we come to that standard algorithm where we put this mysterious 0 in. So far, everything that we've done is visual and kids can see where the numbers actually come from. So now I'm going to, yes.
We have a question that I think would fit nicely here. So how important is knowing the multiplication facts before going to double-digit multiplication? Or is it okay for them to use a grid?
Great question. So my thought on that is we want students to know those facts, right? Like that is something we want them to know. However, we know that not all students are going to learn those facts at the same rate that others do. And so we don't want to impede their future learning because they're still stuck on their single digit multiplication. So it's okay to give them a chart where they can then use that chart. That chart is only going to help them start to make sense of the actual single digit multiplication. It's not going to help them with this process. And we don't want them to get lost in the process because they're so worried about that single digit multiplication. Yes, that is something we would concurrently work on. You might use some flashcards. You might use some games for them to practice, and you keep working at those facts, but we don't want to stop everything until kids have those facts down. So great question. So
I have one more for you. Would it be helpful to do the partial products in the order of the standard algorithm? So doing all of the one place value and then the tens place value.
So it actually is easier for students to add up the digits, add up the products, if they actually start with their tens place, with their larger values, because it then puts those numbers in an order that's easier for them to add. At this point, the order doesn't matter. They can work with the parts that they know, because eventually they start to see that it's all going to go back together. So then we get to lattice multiplication. Now, if you've never seen lattice multiplication, it's very different. Not all kids will use lattice multiplication, but it certainly works for some children. They really make sense of this strategy. I will tell you, as someone who really understands math fairly well, when I first saw it, I was very confused by it, but the student I had moved in from another district where the student had learned this, and I said, you are getting the right answer every time. It's my job to figure out what's going on in this math, but it works for you. So for now, I want you to keep using it, and I will figure out this strategy. It's actually quite interesting once you learn why it works. So the first thing, we're going to still use our 32 times 26. And one of the first things we have to talk about, though, before we get into the process of the lattice multiplication, is When I multiply a ones digit by a ones digit, so when I multiply anywhere from 1 through 9, the largest answer that I can get is a number, a solution, that is in the tens and ones place. So if I think about the largest ones digits I know, 9. 9 times 9 is 81. So the largest amount that it's going to give me is something in the tens place. If I multiply a ones digit times a tens digit, the largest value that I can get is going to be something in the hundreds. And when I multiply something in the tens by something in the tens, I can get to the thousands. So that's important to know for lattice multiplication, because when we set this up, in lattice multiplication, you set up I'm working with a 2-digit number by a 2-digit number, so I'm making a 2 by 2 array or 2 by 2 rectangle here. And I'm really just writing the digits. So we start to get away from this 3 really means 30, but I'm going to think about it as a 3. One of the important pieces in lattice multiplication are these diagonals. And students who really succeed well in this lattice multiplication are so quick and can do it as fast this way as students who do standard algorithm. When we look at this number, 32 times 26, 2 and 6, these are our ones digits. And we know that when we multiply 2 ones digits, the largest value we can have is something in the tens place. So when I look at 2 times 6, 2 times 6 is 12. I'm going to write 12 across this divided line because this place right here is actually my ones place. This diagonal is going to be my tens place. This diagonal is going to be my hundreds place. And this will be my thousands. I'll move that out of the way. So when I'm looking at this, a 1 digit times a 1-digit number could give me a number in the ones and a number in the tens. When I multiply a ones digit by a tens digit, I'm going to get things that are in my tens and in my hundreds. When I do, again, tens times 1, I'm getting something in my tens place and my hundreds place. And if I'm multiplying a tens digit times a tens digit, I could get something that's either in the hundreds or up into the thousands. So if students start to see this as place value, we can connect this to our partial products. So we had 2 times 6 was 12. Well, we saw that in our partial products. This 2 times 2 is 4. But really, it's 2 times 20 is 40, 4 tens. And we saw that in our partial product. Now we're going to move over here. We have 3 times 6 is 18. This is really 30 times 6. So it's 180. So 180 and a 0 in our ones place. And this is 3 times 2 is 6, but it's 30 times 20 is 600. These diagonals allow us to add up the digits, so much like a standard algorithm. 2, there's nothing else to add. There's a 2 here in the ones place. 4 plus 1 plus 8 is going to be 13, so I'm going to put my 3, carry the 1. 1 plus 6 plus 1 is 8, and there's no thousands up here. So then I'm going to read my number, and I get 832. So there's a lot of understanding. Most times, unfortunately, when lattice multiplication is introduced to students, it's here's the lattice and just here multiply single digits by single digits. And there's no building in of this place value idea, and it's not connected to partial products. And then from here, students may move into that standard algorithm. So 32 times 26. So students would have our 32 times 26. So we're going to think about this, how it connects to our either lattice or the partial products. 6 times 2 is 12. So there's a 2 in the ones place. I'm going to carry into the tens. 6 times 3, well, that's really 30, but I'm thinking about it as 6 times 3 is 18. Plus 1 more is 19. I'm moving over, so now this isn't really a 2, it's really 20, and so I'm moving into my tens place, so that's where that placeholder 0 comes from. Because I'm moving to the tens place, my answers are going to start here in the tens place. 2 times 2 is 4, so that was 20 times 2, there's my 40. 2 times 3 is 6, so 20 times 30 is 600. And then I'm going to add 832. But if we don't talk about place value and students don't make this connection about we're moving to our tens, this placeholder 0 really means nothing to them. It just means that I've got to put something there. And in fact, I've actually seen worksheets where like this is set up and it's like I set out for students to do the work, and there's actually a box here that says like put the 0 in there. And we want students to understand why it works. So Michelle, how about questions that came up?
So I have another question about the use of a calculator. And they're wondering, at what grade is it okay to let kids use a calculator?
So I think it's going to go back to the same thing about using the multiplication chart, right? We want students to have that. Part of letting students use a calculator, students also need to know that the answer that the calculator reads is correct. Because how often, I know I do it, I put numbers into a calculator and it gives me back an answer and I look at it and go, well, that doesn't even make sense. So I've typed something wrong or something had already been in my calculator. So again, if we're moving on to larger numbers, we still want them to get down the strategies and the process. But if they're trying to use multiplication for another reason, if you're not working on teaching a strategy, they could use a calculator. The reality is we grab a calculator, we all have them on our phones and we use them all the time. And so using a calculator is not a bad thing, but if you're trying to teach the strategy, you want students to be able to do that strategy and still be making sense of the numbers and the facts and the place value.
There's a request for you maybe to do another example of the lattice multiplication, but use different colors so that it's clearer for place value.
All right.
My suggestion is showing one with the decimals, because sometimes decimals with lattice throw people off, but it's really not that hard.
Sure, I can put a decimal in here. So we'll do 1 4/10 times 3 5/10. All right, so let me try. We'll get it all nice and colorful here. All right. All right, so we put our numbers the same way up top, and I'm going to put my decimal here so that I can see it. And it does not matter, again, which number goes on which side. And if you had numbers that were different lengths, so I probably should have done, let me see if I can adjust real quick. We're gonna. Oop, wrong color. So even if you have numbers that are not the same length in digits, so now I have this 3-digit number times this 2-digit number, really it's got decimals in it, but you can just make the boxes that you need to represent the number. So in this,
the blue and red look very much the same.
They do, okay.
Thank you.
Let's see if you can see my green. I don't know if the green will work or not. Can you see the green? Yes, okay, I got yeses. All right, so we have our diagonals drawn. We have our numbers written on both sides. So we're gonna multiply, and we're thinking about them as individual digits. So in this case, 4 times 5 is 20. So 10s and 1s. 4 times 3 is 12. So I only have to think when I'm doing lattice multiplication, I've taken away that place value understanding while I'm multiplying the digits. And the reason lattice works is because of place value, but when I'm actually doing this, I'm not thinking about this 5 being 5/10, because when we do this, we're now looking at, this is a tenths times a tenths. We're going to get something into the hundredths, and we'll see that in a moment. So then 3 times 1 is 3. 1 times 5 is 5. 2 times 3 is 6. 2 times 5 is 10. And now I'm going to add along this diagonal. So in this case, it's just the 0. In this diagonal, I have 2 plus 2 plus 5 is 9. 1 plus 3 plus 0 plus 0 is 4. 0 plus 6 plus 1 is 7. And I have the 0 here. Now we have a decimal here, so we've got to take care of these decimals. So we've kind of put the decimals to the side, just like when we do standard algorithm. Now we're going to think about these decimals. We're bringing these decimals together. So we're going to bring that decimal down, and we're going to slide this one across to wherever they meet. So these two here come together and meet here. Then we slide down the diagonal, and the decimal goes here. So when we look at that, if you know that in our standard algorithm, usually we multiply like the decimals aren't there. Then we count up how many numbers are after the decimal, and we move our decimal point over that many numbers, right? It's just a bunch of rules that we follow, and we haven't made sense of why that works. But in this case, same thing. There's one number here after the decimal, one number here after the decimal. There are 2 numbers after the decimal in my answer. And that happens because a number in the tenths times a number in the tenths can get us to a place where we have numbers in the hundredths. So this is the hundredths, the tenths, the ones, the tens, the hundreds. And if we think about, we could have something up here into our hundreds, but we don't have anything that carries over because we have something in our tens and something in our ones. So we don't have anything there. So our answer, we read down and then across. Definitely a very different way of doing math if you have not ever seen lattice multiplication before. It's definitely different. Any other questions?
I'm not seeing any new questions in the chat box.
Perfect. Well, we will go on to looking at some of the games and routines. I always like to share a game and a routine that you can do with students. So let me get to our game idea. I'm going to share my screen again. So the game idea that I have for you this week is called multiplication squares. Now, think back to maybe when you were a kid and you played the game, the dot game, where you had this paper with all these rows and columns of dots, and you took turns with a partner back and forth, and you drew a line, and then they drew a line, and then you drew a line, and eventually you wanted to close in the box, and whoever closed in the box got to claim the box with like their initial, or they got to color it in with their color. Well, multiplication squares really is essentially the same thing, except you're going to practice multiplication facts. So instead of using flashcards or a time test, this is just one way that you could practice multiplication. If you Google multiplication squares, you will come up with a lot of these different game boards, and you can find them for free. You can find ones you pay for. You could in fact create your own. If you had a piece of grid paper, you could use the grid paper to do that. Now, I will tell you, see if I can get my mouse here. Here we are. So this game board here only goes up to dice because you use 2 die. So you use a pair of dice, and you would roll them and you multiply the 2 numbers to get the product. You then find the product on the board and you connect the dots just one side of that number. So let me see if I can, I don't think I can annotate here. On my own board, I can't. So if I have 2 die and I roll them and I get a 5 and a 4, 5 times 4 is 20. So I'm going to find a 20 on the game board. So I found a 20 here. I'm going to, with my color or my marker, I'm going to draw from either this side or I could pick this side. I'm only going to connect 1. So then the next person rolls, they get 5 times 5. So they know that's 25. They could come over here and they can connect here. They could find another 25 and start somewhere else. But eventually, now this is a game that will take a very long time. So if you want to create your own board, you can, and that might make it smaller. You might find smaller boards when you Google that. But this is set up for 2 6-sided die. This multiplication square over here is set up to use 2 10-sided die because the numbers are different, right? I'm not going to have 100 over here on this game board because my products can only go to 36. I can, at the most, with 6-sided die, roll a 6 times a 6. Over here, if I have a 10-sided die or 2 10-sided die, I can roll and I could get 100, or I might get 9 times 9 is 81, 7 and a 10 for 70. So make sure that your board matches the die or the dice that you have. Now, I did want to show you a place where you can get the die. Are you seeing my computer screen? Perfect. So again, here I just Googled multiplication squares, and you can see all kinds of images pop up. And some of these are to paid sites, some of them are free. You just have to kind of click around, but make sure whichever game board you pick is one that you can use, you have the right dice for. If you need dice, not all of us have 10-sided die laying around the house or 12-sided die. One of the websites that has different dice on it that you can choose is this website called toytheater.com. I shared this a few sessions ago, but again, it's toytheater.com. And when you go there, you have these virtual manipulatives. And I can scroll down and I can find the dice. And once I'm in here, I can select how many dice I want, up to 5. So in this game, I would use 2. I also can select how many sides it has. So this die here is a 4-sided die. This one is 6. I believe this one might be 8. And this one is 10. This one looks like it's 12. So I'm going to pick 2 of the 10-sided die. and I'm going to roll them. And now I have a 9 and a 2. 9 times 2, 18. I'm going to find 18 on my board. So you could play this. Students could play this at home. Students can play this against each other. You could play this against somebody. If you were playing against them on the computer, you would just have to have your screen in a, like, you each had a copy of the game board, and you could be marking those down. A student could play this by themselves. Not that it would be a ton of fun. They want to play against somebody. You could also have 3 people play this together. You could have multiple people. They just use a different color pencil or pen. I recommend color pencil. You can erase it. And then you can just continue to play. So if you don't have the dice that you need, you can certainly get them here on the toytheater.com. But if you have them, even better, students can play this. You may think about, if we're in this, I know the school year is kind of coming to an end for this school year, but if these were resources that you had at school, you might be able to send home packets to children that have all the materials for the game, but they're all here. Questions about multiplication squares? And if not, we're going to move on to a routine I want to share. Let's see if I can get back. We're back to the PowerPoint, I believe. Open middle is one of the routines that I want to share with you today. And this one, again, is on the web, openmiddle.com. This is some work put together by Robert Kaplinski. They are problems that have multiple solution strategies and really are very open-ended for students. So this is one example, and I'll take you to the website in just a moment. But this one is, when you think about using the digits, it says you may use the digits 0 through 9 once in any of the blank boxes. And in this case, they say that the answer 84 does not eliminate the 8 or the 4. So Daniel was making chocolate cookies. He has 2 digits, so blank, blank, cookies in each row and 2-digit, many rows. There were a total of 84 cookies. How many cookies were there in each row, and how many rows of cookies were there? Draw a model to support your answer. So students are using the digits 0 through 9. They can only use them once in this problem. So I'm looking for how many rows and how many cookies in each row to make a total of 84. Now, on the Open Middle website, there are actually little tiny cards that you can cut out, because this actually can be printed. You can print these problems as a worksheet where they could put in these pieces. But they have these little tiny cards, and if you can see in my picture here, they're all little cards. So kids can actually play around with these cards on the table in front of them and keep trying the problem out. So I want to just share with you, there's multiple solutions. There's only so many solutions, but there are multiple solutions to many of these problems. Some of them are limitless, but some are very specific. So you yourself would have to know a solution or know a way to figure out whether a student's solution was correct. But students can really go at this open-endedly. I am going to bounce back to my website. Maybe it will let me here. So this is openmiddle.com. You can, I believe that was probably a 4th grade problem that I grabbed, but you can see up here along the top, you can pick which grade level you were thinking about working with. So I'm going to go to 3rd grade, and I'm going to think about operations and algebraic thinking. So it's by strand. Oh, right here. This was where I got it from 3rd grade. So a student might actually want to use tiles to act out this problem, and then they might have these number tiles if they want to solve the problem. But when you click on the problem itself, there are some hints. It does give you an answer so that you can see where the answer, what an answer might be. I'm going to go back here. Using the digits 1 to 9, at most 1 time each. So sometimes it tells you you can use the numbers multiple times. In this case, it's saying you can't. Fill in the blanks to make the following problem true. Sarah planted a 2 digits number of carrots in her garden. She planted them in blank rows. Each row had blank carrots. So this one might be a great beginner problem for 3rd grade, whereas this one might be a little more challenging, because I could make up the problem. Sarah planted 12 carrots in her garden. She planted them in 3 rows. Each row had 4 carrots. And so I've only used 1, 2, 3, and 4, and I've only used them once each. So these are just different. There's all kinds of different types of problems that students can use, but there's multiple solution strategies. And it's definitely something that will push students to have to think, because they're not given the information. They're not just, I call them number pluckers. They're not just plucking out the number, or they're not just plugging and chugging through the work. They actually have to make sense of the problem and fill in those blanks with numbers that make sense.
Jen, the question
Yes.
I have is Open Middle free to use?
Yes, I meant to say that this time. Yes, Open Middle is a free resource. And again, you have all the different grade levels up here. It goes right up through 8th grade high school. You can find the different strands, but it is a free resource to use. And let's see, I believe you can print off these problems. And oh, here's the number tiles as well. So there's the printable number tiles. And if you work with older grades that might use the negative, the integers, you actually can print off integer tiles as well. They go from -9 to +9. So you can use those as a resource. Any other questions, Michelle? We certainly have filled our hour today, and I thank you so much for kind of being with us for multiplication. I get really excited about this math because there's so many new strategies, and I was not ever taught this way. And so to me, it's really some new learning and new ways to think about things. So before you go today, here is the survey link, and I will drop that survey link into the chat box so that you can hopefully click it and go direct. Let's see. There it is. And thank you,
And
Michelle.
I dropped it in the.
Perfect. We'll grab it there again. And again, you can always scan the link here. You can go to the bit.ly. If you're watching this through a video, we have learned that if you leave off the https:// and just type in the bit.ly site itself into the address bar, it should work. If you have trouble getting to the link at any time, please feel free to email me. I can always shoot you out that link direct, and that you can fill that out for your contact hours. I will work on getting contact hours out to everyone. However, it will take me the good bit of a week. If you have done any of the sessions 1, 2, and 3, by now you should have your contact hours for all of those. I am finally caught up. So please, if you haven't gotten those, feel free to email me and I can find that for you. Or if you need the links, let me know. But again, it will take a little bit of time for me to get this week's out, as we are always doing trainings and need to get those certificates out as well. So thank you all for attending. I'm going to stop my share. And if you have any questions or need help with that link, let me know.